Not all batteries are created equal. Even batteries that look the same might not act the same because of things like age or temperature. And I'm going to prove it. I've had this drill for 10 years and the battery's getting pretty sad. But I got lucky and found an identical battery that's brand new. So I have identical drills and batteries, except one's old and one's new. And our test is going to be to see how many screws I can screw into this board with the old battery and how many screws we can screw into one of these boards with the new battery. For this, I'm going to need my stunt double and power expert, Brian. Brian, thanks for being here.
Hey, great to be here.
How many screws do you think we'll get with the old battery and the new battery?
That's a good question. I will go with 50 for the old and 75 for the new.
Okay. I have some predictions as well, but let's bring in Michelle. We're going to see Michelle later for some DC to DC testing. Michelle, how many do you think we're going to get?
You know, I think it's going to be just a little bit higher. I think it's going to be 124 for the old battery and 157 for the new battery.
Okay, that is oddly specific, but I like it. I'm thinking we're also about 150 and 100. That's my prediction. Let's see what happens. Ready to get drilling?
Let's go.
All right. It's going to be really embarrassing if I don't get this right on the first try. Dang it. There we go. All right, let's go. So why is an old battery not as good as a new battery?
That's a good question. So every time a battery is cycled, some of its active materials are consumed and thus reducing its capacity. Plus, cycling a battery causes its internal resistance to increase. Both of those factors lower runtime.
Okay, so basically the chemistry starts to wear out.
Yep.
And then the internal resistance goes up, meaning it loses power faster?
Yep, absolutely. Absolutely.
Okay, so let's see how many screws I can get in with the new battery.
Let's do it.
So that old battery's pretty bad. It did 39 less screws. That's 37% less capacity in our old battery compared to our new battery. Okay, so we know there's a difference in our battery performance. These batteries are identical, but this one's been in use for years and this one hasn't. There are other things that impact battery life that we're testing today, like temperature and current draw. There's a test finishing up behind me right now in the temperature chamber, and yeah, I know these are drill batteries, but this isn't just about drills. What we're doing applies to IoT devices. You want to know what your design will do with fresh batteries and how it's going to work with old batteries and hot batteries and cold batteries and low charge batteries and full batteries. I'm now the Dr. Seuss of battery descriptions. So if you want to be sure that your battery-powered device will work with imperfect batteries, there's a couple more scientific, rigorous ways to do that. The first option is to have a suitcase full of batteries. Some at half charge, some should be old, some are new, some are cold, and you can test in those situations. Ultimately, though, that's not very practical or sustainable. There are better ways to test batteries, and that's to create a battery model that represents how a battery behaves in these conditions, and then use that model to test your device. It takes a while to test a model. Each run takes a few hours each. So we spent the last couple weeks creating battery models. It's been all hands on deck. Once you have a model, though, you don't ever need to make it again. So if my IoT device has a firmware update that doubles or halves the Wi-Fi usage, I can use that same battery model to test performance. Or maybe I have a prototype saw that I want to run off these batteries instead of a drill. The same battery model works for every device I want to plug in. So we've built a bunch of battery models. This one just finished up in the temperature chamber. And we've also created a model for current draw. So let's head upstairs where Brian's setting up and we can look at the results of this and other tests. So we're here set up to build a battery model. Walk me through how we built these and what we're looking for.
Absolutely. So we have a profiler opened here.
And we're running on this electronic load and power supply.
That's right. So we have the battery connected right now. So yeah, it's an integrated power supply and electronic load. So right now it's functioning as an electronic load, right? So it can draw current from the battery to build out a profile. Let me go through some key settings here. Obviously, we're going to set the battery type to rechargeable. And then the software can discharge the battery using constant current, constant power, or constant resistance. Or it can utilize a dynamic waveform. So I loaded this waveform And you can see the current spikes, and this could represent a device like a power tool.
So like the drill every time you screw in a screw. Yep. Okay.
But for simplicity's sake, to build our profiles, we just use constant current. Let me update the capacity rating to 4.8, which is the rating of the battery. But as you'll see, the actual capacity is very dependent on how you discharge the battery.
Yeah, and it seems to depend on temperature and on age and on even your load current, which are things that we've built models for. We haven't really analyzed them yet, but we're going to open them up and see what they look like.
Absolutely, absolutely. So that's where this setting comes into effect. You can tie the battery profile to an ambient temperature. You can either manually input it, or you can get it from a DAC, which we did down in the temperature chamber.
Yeah, so down in the temperature chamber, we had the leads going in the chamber to the battery, but we also had a thermocouple hooked up to the battery that then would correlate the power measurements to the temperature.
And that's a very valuable, right? Because battery capacity can vary greatly with temperature, as we will see. All right.
The question is how much?
How much, right? So now let's go ahead and get started and start profiling.
All right. So when I look at this, there's a couple charts here, and there's like a weird spike right up front, and then it goes into like a normal mode. What is it doing first, and then what is that? I'm assuming the normal acquisition mode.
Right. So this is where the spike you saw is actually spiking the battery to measure the internal resistance. And now you can see it's discharging the battery at 500 milliamps.
Okay.
Right.
So here we have on the left side, we have yellow is milliamps, and it's right around 500 milliamps like we'd expect, because that's what we set it to. And then it's measuring the battery voltage.
That's correct.
Well loaded in blue?
Yes. That's
Okay.
correct. That's correct.
But then we also have a cutoff. We told it, if you look on the left side of the screen here, at 12 volts it should stop. And then that bottom chart, I assume it's going to fill up over time. Maybe we come back to that for our first test, because I think that one takes a while.
It does take a while.
The whole thing takes a while. So we actually have built a bunch of these models. We did an old versus new comparison with the drill batteries. We have our screws over there. We also have battery models for old versus new?
Yep, absolutely, absolutely.
All right, so let's take a look at the results of that test.
Okay, let's do it. Let's do it. All right, let me click stop here, and we'll go over to the emulate mode to see a completed profile.
So we've pulled up the new battery model. This is a brand spanking new battery that's never been used. This is an idealistic version of what the battery should be. And then we can compare this to the old battery. So what does our new battery look like? How's it perform?
Well, a couple things to note. So if you look at the capacity rating, what it actually turned out to be is about 1.2 amp hours, right?
Instead of 4.8.
Instead of 4.8, right? So by discharging at 500 milliamps, it greatly decreased the capacity.
Looking at the voltage profile, it really seems like this is not actually a 4.8 amp hour battery, but since we're using identical batteries for all our tests are still going to be valid. What else do you see?
Okay, so here is the actually completed profile, right? So here you can see the state of charge from 0 to 100%, and you can see how the open circuit voltage and the internal resistance vary. So in profiler mode, it measured the open circuit voltage and the internal resistance at each state of charge.
And that actually changes with charge state. That's something I didn't really know before.
Yep. So you can see how the open circuit voltage decreases significantly with time. But another key thing is the internal resistance. For the new battery, you can see it's fairly constant until it gets to around 5% charge left.
Okay, so in our middle ground here, what's our open circuit voltage and our internal resistance?
So in middle ground, around 50%, it's around 15 volts, and the internal resistance is around 200 milliamps.
Okay.
223 milliamps.
So we can compare this then to the old battery profile. Why don't we pull that up and see what changes?
Okay, sounds good.
That looks very different.
Oh, that's very different.
That's significantly different. So let's, before we get to that crazy stuff happening on the left side of the chart, let's look at right at 50%, what's our open circuit voltage and what is our internal resistance?
So the open circuit voltage is around 15 volts, but the internal resistance is around 500 milliohms.
Okay,
almost
so
double, or double, yeah.
So our voltage stayed roughly the same-ish.
Yep.
But double the internal resistance is significant.
Right.
And then what's happening down in the low charge range? What in the world is going on there?
So you can see, around 80%, the internal resistance starts to rise, and then it accelerates. And towards the low end, it really accelerates.
Okay.
Right? I just think about like an old smartphone. Sometimes when you get to the end of the battery life, it just suddenly dies. I don't know. Have you ever had that happen?
Yeah, even with that drill, like I said, I've had that drill for 10 years, and I finally had to get a new battery because I'd get halfway through and it was fine. and then it would just struggle and struggle. So maybe even like percentage on your phone. That's why older phones, run out of the last 50% faster.
Yeah. Yep. I mean, this behavior is consistent across batteries and types.
So why is the internal resistance such a factor in terms of battery performance?
Well, obviously, with a higher internal resistance, there's less power that reaches the device because it's being burned up in the battery.
Sure.
Right, which can increase, the temperature of the battery, and obviously a lower performance.
Okay. Is there like a power loss? Could you multiply voltage by internal resistance? And I guess that's where the heat comes from too in the battery.
Right. Yes.
So clearly the new battery looks a lot better than the old battery. So is this difference a factor of like the chemistry of the battery? What's happening?
It's really a factor of cycling the battery. So every time you cycle a battery, some of its active materials are consumed. So that's where you can see the capacity rating is now decreased to 768 milliamp hours. So a significant decrease. Plus, every time you cycle the battery, the internal resistance increases.
Okay.
Right? So these two factors really deplete the battery runtime.
This is interesting. So that almost aligns perfectly as a percentage to what we saw with the screws, where it's almost 2/3 of the capacity. And maybe as a designer, if I'm figuring out what battery to put in, I would put in a slightly larger battery just to reduce the number of cycles it might have to go through, and that would increase my product lifespan.
Or if there's a minimal acceptable battery runtime, right, you might want to plan for that, right? You don't want, after 2 months of usage and cycling the battery, it's already reached that, right? So that's where you might decide, hey, I need to put in a bigger battery also, right?
Yeah, so basically giving yourself some headroom so as your battery ages, you still get the full performance that your device needs, even if early on in the life cycle you have more battery than you actually want.
Yep.
So old versus new battery, I think we've got that pretty well established. Let's move on to our next test. Temperature?
Sounds good to me.
All right. So for this test, we're going to see how the ambient temperature impacts battery performance. And for consistency for the rest of our tests, we're only going to use brand new batteries. We're going to leave the old battery on my shelf, never to be used again.
Exactly.
So what temperature is this one?
So this was room temp. It had a capacity rating of about 1.2 amp hours.
Okay.
At room temp, with a 500 milliamp current drain.
Okay, and we're going to keep a 500 milliamp current drain. Mm-hmm. Let's see what happens if we go hot. So we did a temperature chamber test at 55C. Mm-hmm. I don't know what that is in Fahrenheit. Put it in chat. And how does that look when the battery gets hot?
Okay, let's pull that one up.
So we ran this one in the temperature chamber with a DAC and a thermocouple. So we actually have a temperature range there. That looks new.
That's right. So the DAC measures the temperature at each point, each state of charge.
Okay.
Right. So you get a temperature range.
And how does our capacity look at 55C versus room temperature?
So you can see it's around 1.1 amp hours. So it's decreased slightly.
Okay. So like 8% maybe off the top of my head?
Maybe. Generally, higher temps don't affect battery capacity as much as lower temps.
Okay. And we did a lower temp one, but I don't want to leave this one behind yet. What else do you see here? Anything interesting?
Well, you can see the open circuit voltage is lower.
Okay. And that's probably my fault that the voltage is lower. We did 2-wire measurements and not 4-wire measurements. So that means we had really long cables going into our chamber, and we're basically running 500 milliamps there and back. And we had voltage loss in the lines. Had we done a 4-wire measurement, there are sense ports on here. We should have maybe done a 4-wire measurement for apples to apples, but I think we maybe I don't know, 0.7 volts loss seems fair to me at this current rating.
Yeah, that's absolutely probably what happened.
Internal resistance?
Internal resistance, you can see, is a little less constant here.
Do you ever feel like you're a sportscaster, but for test and measurement? 'Cause that's how I feel right now.
That's how I that's how I roll it. Okay. That's how I roll.
So to summarize, the higher temperature impacted it a bit, but 5 or 10%, probably not significant in the grand scheme of things. What does it look like when we go cold?
Okay, let's check that out. Pretty wild.
So this was at 0 degrees Celsius.
That's right.
I should have set this up, but I'm so distracted by the chart. Yes. What is happening?
Well, you can see the internal resistance. Wow, it's really spikes here at around right after 40% state of charge. It's not nearly as consistent. And you can see the capacity ratings now dropped about 1 amp hour.
Okay, looking at that chart, I thought the capacity rating was going to be lower than that. But we see a significant drop in the open circuit voltage.
That's right. And a huge spike in internal resistance, right?
Huge.
This is the first time I'm looking at this. This is the first time I'm looking at these charts.
Me too. That's crazy.
Those are crazy.
Look it up. Let's look it up.
Okay.
Keep it rolling. It seems like we're kind of stumped here, Brian. What is there someone who we can talk to?
I know exactly who we should talk to. Let me hop out and give my battery guru a call.
Okay, is this Paul?
This is Paul.
Okay, let's hop on a call with him. You can, go wherever you take phone calls from.
I'll be right back.
And we'll get to the bottom of this.
And you can see the internal resistance, right? I mean, it's for 200 milliohms versus 500, but then there's this wild spike up to 1.28, and then it goes back down.
It's telling me that the temperature, one of those cells is not liking that 0 degrees or whatever the temperature that you were using. That's what that's telling me.
We did it. We solved it.
All right.
How excited are you?
I'm pumped.
Yes. Okay. I can tell. Okay. So clearly this is a funky looking chart, but this is hard data. So can you kind of talk me through at least the impact on capacity rating?
Yeah, so absolutely. So here you can see the capacity rating has decreased around 1 amp hour from 1.2 amp hour. And then also you can see the internal resistance has increased. So at about 50% charge, it's also at about 500 milliohms, which is similar to what the old battery exhibited.
Almost double the internal resistance before we even get into that weird range of happenings.
And this is why battery runtime is so affected by cold temps. I mean, you see stories about this with EVs struggling in cold weather, and this affects any battery-operated device.
Yeah, I know I see it on my e-bike, like when I'm riding in the snow and the cold here in Colorado, I don't get nearly as far as I do in the summer, and I get a lot farther on the same charge. So cold has an impact.
Absolutely, absolutely.
So what's our final test here for these batteries?
So our final test is looking at how battery runtime is affected by the level of current drain.
Okay, so if you pull more or less current, what's your equivalent capacity?
Absolutely, absolutely.
Okay, let's pull up those models and see what it looks like.
Okay, let's do it.
So this is test number 3. We've been pulling 500 milliamps constant load. We wanted to see what it would do to the capacity if we dropped that load, basically less stress on the battery, more chance for electron mobility to kick in and potentially give us more capacity. So we ran it at 250 milliamps and 100 milliamps. What are we seeing at 250?
So at 250, the capacity rating has increased to around 1.4 amp hours. So a pretty significant increase.
It's like 0.2 amp hours.
Yep, 0.2 amp hours. If you look at the battery model, it's pretty similar, right? So you can see here. Yeah, so the internal resistance is pretty consistent, around 10% discharge. So it's basically the same battery model, but just higher capacity.
That's like, when I look at this battery resistance, we were seeing about 220, 230 on the room temperature, and now we're seeing like 180, 190.
So it's decreased a little bit.
Yeah, 15%.
Yeah, that's true. That's true.
What does it look like at 100 milliamps?
So at 100 milliamps.
And this test took a long time. About right. 5 times as long, would you say, as the 500 milliamp test?
Yes, you had to be patient with this test. Yeah. So here at 100 milliamp discharge rate, it's around 1.4 amp hours. So a slight increase over the 250 milliamp. But you can see it's not perfectly linear.
Oh, yeah, linear meaning how much current you pull versus your capacity. Yeah. It's not a nice line.
Yeah, it's not going to be a nice line.
And that would impact your battery selection based on how much current you're going to have to pull at a time. But at the end of the day, it's pretty clear that if you pull more current, your effective battery capacity is lower. And this data also helps confirm it's probably not a 4.2 amp hour battery. So it's really important to make sure you're actually getting the effective capacity out of your battery that you think you're getting. And you should design and spec batteries into your device based on your current draw and your battery's effective capacity at that current draw.
That's where it's important to optimize your device around battery life.
So clearly a 500 milliamp draw was not great for this, but if we could get our device to run at like 250 milliamps, that would give us an extra 10% of battery life.
And that's why you want to optimize your device to minimize the current drain.
And now if you were optimizing, say, an IoT device for pulling Wi-Fi packets, this model becomes invaluable to you because you don't have to run this super long test every time you update your firmware.
Right. So now you have a known good reference for this set of battery parameters.
And we have that model loaded into the power supply, and you hook up your device here, and it acts as if it's this battery.
Yep, it emulates the battery.
So I don't need a suitcase of batteries after all.
No. You can use that suitcase actually to go on a trip.
Okay. Well, I guess I need the suitcase of batteries one time, but not every time I need to test everything.
No. No.
Okay.
Yep.
So we've built battery models for 3 different scenarios and analyzed them. Old versus new batteries, temperature, hot versus cold,
Yep.
and we have models for high drain, low drain, current applications.
Yep.
The models are no good if we can't actually use them. So let's take our drill. We have some DMM probes that we've repurposed to be leads for our drill, and we should be able to emulate batteries.
Absolutely, absolutely.
So what's our test going to look like here?
So here's what I propose. Let's look at what happens at 5% charge with a new battery versus the old battery.
Okay.
Will the old battery still work, right? Let's find out. And we can do that quickly.
So set that up now. I see a 50%.
Okay, it's going to take a while. It's going to take a while here. Boom, 5% charge right there.
Okay, let me get these hooked up.
Okay.
These things made you bleed.
They did. It's, you don't want to close up my hands.
Okay, and we got to drill a screw in. So let me get the wood and the screws. So what are we looking at right now? What's our state?
So I got the new battery loaded here at 5% charge.
Okay.
So you can see the internal resistance is about 300 milliohms.
And our voltage?
Our voltage is around 13.6 volts.
Okay. And the batteries were rated for 14.4, so it's still a little under rated.
Right.
But probably still going to work, right?
I think so.
Okay.
Let's find out.
Let's give it a go. 5% new battery.
Yep.
It's going.
Wow, like butter.
That was like butter, and you can hear the thing working. So we can actually see, we have a 20 amp limit, but we can see it spiking pretty hard.
Yep, absolutely, absolutely.
Okay, so the new one went in. Hopefully I didn't drill right into my table. It's going to be close. What's our next setup?
All right, now let me stop this, and let's switch over to the old battery.
Okay, so this is the old battery
Yep.
at 5%.
At 5%.
So instead of having to have a new battery discharged down to 5% to test this and having an old battery discharged down to 5% to test this, we just used that profile, that model, loaded in, and we're ready?
We're ready.
Okay.
Ready
Hit start.
To go. All right.
Ooh, it really struggled at 5%.
Absolutely, it drained pretty quick. So it's struggling.
Okay, so there you go. That was way easier than swapping in new batteries.
I think so. I think so.
So I hear you brought some other devices we can do this with and some other battery models. What else do you have for us?
So I have some IoT devices that we can play around with, where you can see as well how battery emulation works and how you can also use an emulated battery for lower power devices.
All right, let's check it out.
Okay, let's do it.
So as much fun as it was screwing around with the drill, this is high power. We were pulling 20 amps. This does really well with low power things too. You know, we could discharge this drill in a morning just by drilling in 106 screws. Trying to discharge some other devices might take months or even years. And that's where this becomes really, really useful for designers. So what did you bring and what are we looking at?
Absolutely. So I brought in this CO2 smoke detector. It's Wi-Fi enabled, so it's a good example of an IoT device.
And I don't want to be changing my smoke detector batteries every day. How long does this last?
It can last a year probably.
Okay.
It can last a while.
So to run a true test like we ran, you don't have 5 years to test 5 batteries.
No,
Okay.
you do not. No, you do not.
And you've profiled a battery. What battery does this run off of?
So it runs off a CR123A battery. You can see here. So we built out this profile.
Okay.
So we're ready to start emulating. So the internal resistance is around, 170 milliohms. And the open circuit voltage ranges from around 4.18, down to around 2.88.
Okay. And so we're going to test it, I assume. What test are we running?
So we're just going to test the current drain, right?
Okay.
So we're going to do some current drain analysis. Right now, it's set to 50%, but let's just switch it to 75% here and start the test.
Sounds good.
All right. Let's start emulating. So now you can hear it start.
It's so loud, right?
It's powerful.
Okay.
So you can see the current spike up to 110 milliamps.
So that's when it turns on. That was probably that beep.
Yep, when it turns on, that's beep. Now it's initializing, so you can see the LED flashing. So that's this current draw you're seeing here.
And it automatically scaled for us there.
Yes, absolutely.
Okay.
So now it's gone into a lower power mode where it's just taking measurements. So again, it's a combination CO2 smoke detector. So you have measurement A here, which is probably in the milliamp range. I'll zoom in later to show you. And then you have even smaller spikes down here. They're probably in the microamp range, or you can see are in the microamp range.
Okay, so a moment ago we were testing at 20 amps, and now we're testing microamps.
That's right.
Which is crazy for power type stuff like this.
It has quite the measurement range. Okay. And here you can see it actually attempting to connect to the Wi-Fi network.
Okay.
So again, spikes up to around 27 milliamps. So let me go ahead and hit stop and do a little analysis.
Okay.
Okay.
Sounds good.
All right. So let me zoom in here. So yeah, you can see when it attempts to connect to the Wi-Fi network, it's at around 28 milliamps. Now let me zoom in on some of the small measurement spikes.
So 28 milliamps, that's probably a pretty big draw for something like this.
Yes.
So you want to limit how often that happens, make sure you're not accidentally pinging Wi-Fi, that sort of thing. Right?
For sure,
or even sending data if you're remoting into this to see how you're, I don't have a vacation home, but if I had a Wi-Fi
Yes.
one, I imagine a vacation home is where I would put it.
Absolutely, absolutely.
Okay.
It could be very useful for that.
Okay.
So now I've zoomed in on the measurement spike. So here's measurement A, which is around 1.68 milliamps, and you can see measurement B is in the microamp range. So this really shows you the wide dynamic current measurement range of the power supply.
How precise can this go? How small?
So it can measure down in the microamp range.
Okay.
So like if you look at the spike, so the peak of spike, it's probably around 126 microamps.
So why would I want to run this for something like a smoke detector, carbon monoxide detector? What is how does this help me?
So it really helps you optimize your battery life. Right? So if you, for example, are developing a new detector and you want to test hardware version A versus hardware version B, or you have, a firmware update, right, that you want to test, and you want to see how that impacts the battery life, right? Or, you've changed how often it connects to the Wi-Fi network, right? And you want to figure out how big of a deal that is for current drain. You can run this analysis and quickly determine the depleted capacity, or really zoom in on individual current spikes, right? So if you were using like a different sensor, right? So there was a new sensor design that you thought could optimize the current drain. You could test it quickly with this and test it at different charge levels.
Yeah, so pretty much anything you roll into this, you can directly correlate to the power consumption and get a really, really good idea of how well your IoT device works.
Absolutely, absolutely. And, as we discussed earlier, I could load in an old battery, right, an aged battery, and quickly test that, right? How does this new design operate after 1 year? I mean, that's very important for a CO2 smoke detector.
Yeah. And even simple things like figuring out when the low battery beep starts going off, stuff like that, you can tweak.
Absolutely, absolutely.
Interesting.
So, yeah, This is a great tool, as you can see, for really optimizing your design for better battery runtime.
Yeah, one of the interesting things here, this is lithium ion. Our drill battery was something different. So we actually have some lithium ion batteries in the chamber running a profile right now. And we'll magically pop back here and check out those profiles.
Sounds good to me.
All right. So we created a couple battery models overnight of our LiPo batteries, which are different than our drilled nickel metal hydride batteries. What did we find out for the LiPos?
Okay, we got some interesting results. So this profile was taken at room temp, right, with a new battery.
Brand new battery.
Brand new battery. So you can see the overall capacity is around 2.8 amp hours, right? And if you look at, like, let's say 50% charge, right, you can see the internal resistance was around 333 milliohms.
All right, and then we also tested a cold battery. So we did one at 0 degrees C. How did that one do? I haven't actually really looked at this yet.
Now let's take a look. So for the cold battery, if you look at the overall capacity, it dropped around 2.68 amp hours.
Okay.
So a slight drop off. And if you look at the internal resistance at 50% charge, it increased around 471 milliohms.
Okay, so about 150 milliohms more internal resistance. Right. Maybe if we tested the LiPos even colder, it almost certainly would have gotten worse.
Yes, for sure.
Okay. And then we also tested a very old and sad battery. I'm going to cover that brand name. This thing has been used quite a bit.
Yep.
We don't really know how many cycles it had, but it was in one of our engineers' houses for like a long time being used. What was it used for?
Headlight flashlight.
Like a headlamp. Okay. They had the same rated milliamp hour.
That's
but
right.
How did it perform?
Oh, pretty bad. Pretty bad. Okay. So you can see there's substantial drop off in terms of the capacity rating. So it dropped to around 1.7 amp hours. Almost half.
That's like 40%.
Yeah.
That's wildly different.
Right.
Okay. I'm shocked by that, actually. I would never use this battery again.
Yep. And then if you look at the internal resistance at around 50%, it's around 764 milliohms.
Okay. So even double and then some what we saw from the new equivalent chemistry battery.
Yep.
Okay.
So substantial performance drop off.
So old batteries are batteries with a D. Yeah.
Yes.
Okay.
Absolutely. And you also see some weird behavior here with the internal resistance, even at higher charges. So
how high did it go?
It jumped up to almost 1.28 ohms.
So that's 4x what we saw here.
Yeah.
So your battery age matters, and you want to make sure you have a device that can handle maybe not this old of a battery, but old batteries.
Yep.
Okay. So we've gotten pretty far into the deep end of battery profiling and emulation, but now we're going to shift our focus a bit to DC converters, and that's why we have Brian and Michelle here for this next bit. Now, it's pretty rare for a device to run on just one voltage level like you get from a battery, and as we saw, a battery's voltage isn't consistent across its discharge cycle. That's where DC converters come in. They'll take a variable voltage input and give you a stable voltage output, well, stable theoretically. So we bought these two cheap DC converters. They're what, like $5 each?
Yeah, just about.
About that.
Okay, and we're going to put them through their paces using 6 different tests. We'll find out how well these work, and we'll see if one of these is better than another. Now, if your devices use DC converters, you want to test them and make sure they're not going to take down your device, and also their efficiency will impact your battery life, which is something else we're going to test. So, Michelle, you brought these in. Tell me a little bit about these converters.
Of course. So converter A is a buck converter and accepts an input voltage of 8 to 22 volts, and it's spec'd at 6 volts, 3 amps output.
Okay, so it steps down from a higher voltage to a lower voltage,
Exactly.
3 amp out spec. What about converter B?
Now, this one is a little bit different. It's a buck boost converter, and it accepts a variable input of 5 to 32 volts. And what's really interesting here is that it has a variable output voltage. So it can go anywhere from 1.25 to 35 volts output.
So kind of anything goes with that one. It's all over the place. And we're going to put these through their paces with Brian. You brought this setup. Tell us what we're using here.
So this is a DC power analyzer, so it's actually a modular power supply. So we have a electronic load module installed as well as a power supply module installed. So you can see the DC converter attached to the front of the DC power analyzer. So we'll be sourcing power from output 3 and syncing power from output 2. The great thing about these modules is that they can measure both current and voltage, so you can make calculations such as efficiency with one box.
All right. And what is our first measurement that we're going to make?
Load regulation.
Awesome. So we don't need the scope for that one, but we'll bring you back when we're ready for the scope.
Sounds great.
All right,
Sounds awesome.
So Brian, what is load regulation and why does it matter?
So load regulation is very critical. So it's looking at how, when you vary the load current, how the output voltage can vary.
Okay. And you have a setup here. Talk me through how we're actually making this measurement.
Sure, absolutely. So I created an automated script. So you can see here that it's going to set the input voltage to 10 volts, and then it will sweep the current from 0 to 4.5 amps in 100 milliamp increments.
So we're just going to step up 100 milliamps at a time, 45 times, and we're going to see how the output voltage changes?
Yes.
Okay.
So how it responds.
Let's hit run.
Okay.
See if it works.
So in theory, it should be around 6 volts and hold steady there.
Sure. That's quite the scripts. The set of scripts here. Is this test flow?
Yes, this is test flow right
Okay.
here. Test flow.
So essentially, we're going to see the performance of the converter at these different current draw levels and see how close to our target 6 volts it is.
Yes. We'll see as it goes out of spec when it will drop below 6 volts.
Okay. And this is useful because if you know how much current your device is pulling, you know how much you're actually going to get out of your DC converter.
Absolutely. Absolutely.
Ooh.
So here you can see, even though the spec was 3 amps, right, it still is able to hold a voltage above 6 volts all the way up to around, all the way up to about 3.8 amps.
Okay.
And then
so
there's you can see a sudden drop off.
Okay, so they kind of almost underspec this one. I'm curious how the same test runs on converter B.
All right, let's check it out.
Converter B is hooked up. Let's see how it handles it.
All right, let's roll.
These actually make for a pretty good drum roll.
There it goes.
Got some reverb. Ooh, it dropped below 6 pretty quick.
Yeah, it did.
And it's okay to have a little bit of wiggle room usually, but you don't want dramatic fall
No.
off.
I mean, this could be a big problem for many applications.
As soon as it started dipping, I heard it make noise.
Look at that.
So immediately we see this converter fail at 3 amps of draw, but we're not quite done yet. Brian brought another way of testing load regulation.
So another method you can use is using an automated waveform generator. So here we have a pulse. So we're just pulsing the load current from 0 to 3 amps.
Okay.
So we're going to see how the output voltage responds.
So before we kind of swept it, now we're just stepping from 0 to 3.
Absolutely. And by using a waveform and using an oscilloscope, we can actually visually zoom in and see the response.
Okay.
Right?
So let's take a look at the scope and see what's happening.
Yeah, absolutely.
So you can see a pretty dramatic spike here when the load kicks in. And we can see our dip is about 730 to 830 millivolts. So I'm curious how this is going to look on this converter. You can actually hear this DC to DC converter changing. So there's like a capacitor doing this or a resonance. That's crazy. So we hooked up converter B. Let's look and see how it performs on the scope. When we look at it, we see a much bigger drop, and it doesn't really even recover back up. So we're seeing about a 2.7 volt peak-to-peak drop and about a 3.2 volt minimum. So the funny thing about this converter is it doesn't actually have a rated load current. So we're probably pushing it over, spec. It's not spec because there is no spec, but it might catch on fire in a moment. So
Yeah, luckily it's only $5.
yeah, $5 is cheap enough to blow, but you wouldn't want to put it in a higher end device, that's for sure.
Yeah.
Okay. All right. What's our next measurement?
Line regulation.
So what is line regulation and why does it matter?
Sure. So line regulation is testing how the output voltage responds to input voltage changes.
Okay.
So think about the battery test, how the voltage changed over the lifespan of the battery, right? It'll be very important for your DC to DC converter to be able to handle that change and maintain a stable output.
Okay. So what is our test specifically? We're using test flow again.
Right.
What are we running?
Sure. So we are going to sweep the input voltage from 6 volts to 40 volts in 1 volt increments and see how the output responds. So if you remember, if you look at the spec, this device is spec from 8 volts to 22 volts. So we'll see how it responds outside of the spec.
So we're going way 18 volts over the spec.
Yeah.
This one was for like 32, so less so.
Yep.
Let's see how converter A does, and then we'll compare it to converter B.
Yep. Let's live on the edge here and go outside of the spec.
Yeah, fortunately we have backups if we blow it
Yes.
up. Because I'm legitimately concerned it might let the smoke out. Okay, how's it look?
So you can see, at 8 volts, when it comes within spec, then all of a sudden the voltage is around 6 volts. And what's shocking here is that even though we went all the way up to an input voltage of 40 volts, it maintained the 6 volt output.
How high can it go?
You want to find out?
Yeah.
Okay.
Do I need eye protection?
Hopefully not. Oh, there we go. Whoa, we found it.
How convenient. It's almost
So around 41 volts is
42
where
volts.
42 volts, yeah, is where it cuts off.
I'm willing to bet converter B doesn't do nearly that well, but let's try it out.
I'm not going to participate in that bet, but yes.
All right, you ready for converter B?
Yes.
Are we going to run it to 50?
Let's do it.
Oh, gosh. Okay. I'm legitimately nervous. I'm going to
Back
hide
away.
behind the power supply. So at first glance, this looks really bad, but you got to watch that y-axis. This is actually only 1 millivolt difference from top to bottom. Our chart ranges from 5.97 volts to 5.98 volts. So converter B easily meets its specification. It does pretty well. The buck boost configuration might be doing it a favor versus just a buck converter. I don't know.
Yeah.
So we tested load regulation to see how our device changes when the load current changes. We tested line regulation to see how our output voltage changes based on line input voltage changes. And then what is our third test?
So it'll be the turn on time test.
Turn on time test. I think we need Michelle for that one.
Yes, come on in, Michelle.
Okay, get out of here.
All right.
So our next test is turn on time. What is that test and why does it matter?
Yeah, so this is a really important test because the turn-on time test measures the time delay between when the input voltage is applied to the DC to DC converter and the time it takes to reach its steady-state output voltage. We want to look out for inrush current when a power supply turns on. This is because when applying power right away, the inductors and capacitors aren't automatically at steady state. They have to charge up, and this can pull a lot of current and damage a system. Turn-on time can also affect the overall performance and efficiency of the converter, especially in applications where quick and reliable power conversion is critical. The longer startup time may result in issues with power sequencing, voltage overshoots, or undervoltage lockouts. So it's really important to perform this test. So we have a couple pieces of gear here. The first is the DC power analyzer, which is powering our DC to DC converter. And then we have the oscilloscope, where we're going to use the power app in order to analyze the voltage changes.
We also hooked up this button between our power supply and our converter so we can toggle the power on and off quickly. Also, I really like playing with this button. Okay, so let's set up the scope and see how this converter A does.
Yeah, let's get started.
All right.
So we're going to open the power analysis software on the oscilloscope. For this, we'll click Analyze. Here, we have the Analyze menu, and we can go to Power Application. There's a ton of different measurements we can make here, but we're going to look at the turn on, turn off time. So this is going to do everything for you. The software is automatic. We just have to tell it a couple of things we need to do with the settings. So first, we're going to verify we are using the turn on test. The signals, so we do have our input, channel 1, hooked up to the DC power analyzer, supplying at 10 volts on channel 1. And then we're monitoring the output of the DC to DC converter on channel 2. So everything looks good here. Next, we'll go into the settings. So here we're going to make a couple changes. The input type is DC. The DC V in, we are supplying 10 volts, so we're going to have 10 volts here. Since our converter is dropping the voltage down to 6 volts, the steady V out will be 6. Now we're ready to run the test. All right, so now it's time for the big red button.
Okay, so this turns the power supply on and off. We want it off?
Yes, to start, we want it off.
Okay, it's off.
All right, perfect. Now we're ready to move on to the next step. Cool. Now we can release it. Let's turn the power on.
Did it work? I can't see it.
I know.
Okay.
It looks like it worked. Microsecond.
Okay.
Really?
Oh man, I can't read either. Can you read that over there?
Oh no. 106 microseconds.
Okay. Wow, that was the worst way to film that. Okay. So 106 microseconds. And it looks pretty normal.
No surprises here. Yeah.
Time for converter B, I think.
Let's test it out.
Okay. It's going to be a small miracle if I wired that correctly because this is quite the setup. Do you want to run through all the settings again?
Actually, we just have to click apply.
Oh, okay. Well, let's click apply. Can you reach?
Yeah. So the power supply is turned off. Click next. All right, let's turn the power supply on.
Okay.
All right, let's analyze this. Can't read it.
Once again, we have not learned from our mistakes.
Wow, that was the worst way to film that.
Oh my. Oh. Ooh. Yeah, so 1.21 milliseconds. So it's an order of magnitude slower than converter A.
Yep.
So you also mentioned overshoot. Can you point that out? You can walk around. You don't have to, I'll spare you.
So as you look at V out, when it reaches 6 volts, it actually goes a little bit above here with the overshoot. So right here.
The hands make me so happy. Like, absurdly happy. So overshoot can be a problem, especially if it's really bad, but in this case, probably not an issue.
Not too bad, but still good to monitor and perform this test so you make sure the order of magnitude on how much it's overshooting doesn't affect your system.
So we did turn on time. I'm assuming our next test is turn off time.
You're absolutely right.
Okay, let's set it up. So our next measurement is turn off time, which I assume is very similar to our last test, turn on time, but what's different? What are we looking for here?
Yeah, so really similar, but turn-off time measures how quickly the converter stops supplying power to the load after the input voltage is removed. This is important because the load may continue to draw power from the output capacitors even after the input voltage is turned off, which can lead to voltage spikes, which can damage the load or the converter itself.
Okay, so for this test, the setup's the same. Why don't you set up the scope? I'll do the button pressing again, I guess.
Sounds great.
Okay.
All right, so the power supply is turned on, so we're going to click Next. Now we can click the button.
Okay.
So the turn off time is 2.3 milliseconds.
Okay.
And as we look at how it turns off from 6 to 0 volts, we don't see any overshoots or undershoots, so it looks pretty good. It's a little bit noisy here, but all things look okay.
So let's try our other converter.
Let's do it. Now we have converter B set up. All right, let's analyze the results. So first reaction here is that the turn-off time for converter B is a lot slower.
Whoa.
Compared to our 2.3 milliseconds, this is 169 milliseconds. So,
Wow. So that's like 2.3 to 170. So that's like 80x slower? But it looks pretty clean.
it looked a lot cleaner than the other one, so.
So the difference between converter A and converter B might matter a lot for power sequencing, both for turn on time and for turn off time. Hey, it's Daniel from the future in the editing bay. I have to address something about this waveform because I was losing sleep. It was bugging me. I couldn't quite figure out what was wrong with it, but I finally did. The cursors here should be measuring the green fall time and they're not quite lined up right, probably because that yellow waveform, which was our power button and our power supply, was bouncing a bit and didn't cut off quite like we wanted it to. But when you look at what this measurement should be, it looks like that fall time on channel 2 is about 5 to 7 milliseconds. So it's not 2.3, it's probably more like 7, but overall, all the other analysis and data is valid, and the comparison of A to B is still valid. It just should be more of a 7 millisecond fall time. So we know how these turn on and off. What else do we want to know about them?
Now we want to measure the ripple output to measure the noise in our system.
Okay, let's set it up. So our next test is output ripple. Can you tell me a little bit about what that is and why it matters?
Of course. So output ripple on a DC to DC converter is mainly caused by the switching action of the converter, which results in the flow of current through the inductors and capacitors in the circuit. Measuring ripple in a DC to DC converter with an oscilloscope is important because ripple can affect the performance and stability of the converter and the system that it powers. The ripple is an AC component superimposed on top of the DC output voltage, and if it's too high, it can cause issues such as noise, EMI, and even damage downstream components in your design.
Awesome. So how do we set this up? How do we run it?
Yeah, so it's pretty simple. We're just going to flip this over to ripple output, and we're going to make the measurement.
All right, let's do it. We're hooked up to converter A. Yeah. Let's set up the scope and see what we get.
All right, so the auto setup is completed. Now we're going to click apply to pull up 2 measurements. So we have 2 measurements that have pulled up. Output ripple, which is a voltage peak-to-peak measurement. This is sitting at around 278 millivolts. And then we have the AC RMS full scale, which is sitting at about 17 millivolts.
Okay, so 17 millivolts RMS. How do you feel about that for this converter?
Yeah, so that's pretty good for this converter because we're looking at a ripple factor of about 0.33.
Okay.
Which is pretty good. So it's that under 1% ripple factor, which is pretty good for a converter.
Yeah, so 1% of this, 6 volts, 1% is 60 millivolts. So it's about 20, so about 0.3. Yeah.
Yeah. So
that math works for me.
I was like...
Let's try converter B.
So we're going to click apply again and run the same test.
Okay. Oh, you know what I have to do first?
Oh, yeah, I was like,
I have to turn on the input and the output.
Yeah.
Okay, what do we get? We had a little trouble setting this one up.
So we performed an auto setup again, and now we're going to click apply for the converter B. And so for converter B, we have an output ripple of 766 millivolts, and then an AC RMS of 24 millivolts. So quite a bit higher than the output ripple on converter A. When we look at AC RMS, they're pretty equal, 17 millivolts versus 24. So both are under 1% ripple factor.
Okay, it's time for another test, and we need Brian back. So for our final test, we want to know how efficient these converters are. Brian, how are we making this test, and what should designers think about when they think about efficiency?
Sure. So efficiency obviously is the power output over the power input, right?
Sure.
And especially for battery-operated devices, this is critical because it can directly impact battery runtime.
Okay. Talk me through our setup. What are we looking
Absolutely. So again, we have the DC to DC converter connected to our DC power analyzer. And here I have a script written where it will test the efficiency by sweeping the voltage and the current.
Yeah.
Okay.
Let's run it and see how they are. Any predictions?
So generally at higher voltages, actually DC to DC converters are more efficient.
Okay. Do you have a prediction for which one will be better?
Oh, I will predict DC to DC converter A.
And I'm going to push you for a number. What percentage better do you think it will be, say, at 20 volts? 'Cause I think we're running to 20 volts. 22 volts.
22 volts. I will go for like 10% better.
10%? Okay.
Yeah, 10%.
I'm going to guess 5%.
Okay.
I'll bet you dinner.
All right. Sounds good.
Okay.
Sounds good.
Let's hit run and see what happens.
Okay. So here we can see the results. So if you look at the x-axis, we have the load current, right, which was swept from 1 amp to 3 amps. And on the y-axis, we have the efficiency. So here you can see the 2 curves. So the white curve represents the efficiency at 8 volts, and the yellow curve represents the efficiency at 22 volts. So you can see they start out at about the same point. So they're both about 90% efficient, about 1 amp. But as you increase the current load, they really separate. So up here, you can see, when the current load is around, 2.4 amps, the efficiency when the VN is 22 volts, it's, almost 86% efficient versus being 81% efficient.
Okay, so at the range which we tested here, we have 8 volts to 22 volts input.
Right.
and 0 amps to 3 amps. We basically tested all the different corner cases of this converter. It did a lot better than I thought it was going to do.
Yep. But if you look at the specifications, it's actually specified to be 95% efficient.
Oh, that's really optimistic.
Yeah.
95%
Yes.
efficient. No, I don't.
No, I don't think so.
Yeah.
This shows the importance of testing this to really understand what the actual efficiency is versus trusting the specification.
Absolutely, especially depending on your current draw. Let's try another converter.
Okay, let's do it.
Okay. So we've hooked up converter B. You predicted 10% worse. I think I predicted 5% worse.
I believe so, yes.
All right, let's see what happens.
Okay, let's go.
So the results are in.
Yes.
What do we see?
So with this DC to DC converter, the efficiency is substantially worse. So if you look at 1 amp, the efficiency is around 78% at the 22 volt setting and around 74%, 75% at the 8 volt setting.
So if you combine our predictions, we were spot on.
Yes.
Okay.
Yes.
So I guess we have to buy each other dinner?
Maybe something like
Someone
that.
else has to buy us.
Something. Yes,
Okay.
absolutely. Absolutely.
What do we see at the higher voltages?
So, you see the same behavior as with the other converter where it is more efficient at higher voltages.
But the efficiency gets really bad in the 8 volt setting when we get higher up. It's like 50, 60% efficiency.
So think of the loss if you use a converter with this low of an efficiency level.
Yeah, and that all comes out as heat. And we've experienced that because we almost burned ourselves a couple times unplugging these and plugging them back in. We have learned a lot about converters so far. Let's recap. It turns out Brian is a much better predictor of performance than we are. You were closest on the screws, so you're pretty close-ish.
Yeah, yes, I was in the ballpark.
Okay.
Luck had nothing to do with it, but I was in the ballpark.
So you planned it all out. Did you test it at home first? Be honest.
Perhaps.
Okay. So in that process, we emulated a bunch of different batteries. What are some of the takeaways for things that impact battery life?
Well, first you have battery age. That can have a significant impact as we saw. Then you have temperature. And then when you actually discharge the battery at different rates, it can also affect the overall capacity.
And then after we did our battery emulation and profiling, we moved on to DC to DC converter testing. We tested converter A versus converter B. What was our first converter test?
Load regulation.
So what is load regulation and what do we learn from it?
So load regulation looks at how the output voltage changes due to changes in the load current.
And we saw converter A do much better than spec. Converter B didn't really have an output current spec and was making some noise. So not long for this world, I think, on that converter.
It struggled a little.
And then our second test was line regulation. And what do we see there?
So line regulation looks at how stable the output is when you make changes to the input voltage.
And then we moved to turn-on testing.
Exactly. And there we were looking at how long it took for our output voltage to reach its steady state after the input voltage was applied. And there we saw that converter B performed a little worse than converter A. There was a small overshoot there, which we don't want because that could discharge into our system. So converter A performed better in this case.
Okay. And then for turn-off testing, there was a much bigger difference.
Yeah, there really was. Converter B took a significantly longer time to turn off.
So we looked at how they turned on and turned off. Next was how clean was the signal, how much ripple was there. What do we see for the ripple performance?
Yeah, so for the ripple performance, when we looked at ACRMS full scale and the ripple factor, they actually performed pretty similarly. Both were under 1%. And so that's pretty good. However, when we looked at output ripple, converter B had a lot more peak-to-peak ripple than converter A.
Yeah, it was interesting to see the RMS about the same, but the peaks be so different.
Yeah.
And then the last test was efficiency. What do we see for efficiency?
So efficiency, A definitely won out, was about, I think, 10 to 15% more efficient than B.
Yeah, this one I think peaked at around 90% efficiency, and that was like 75% efficiency. So ultimately, converter A seems like a much better option than converter B, which didn't even have an output rated current. We saw it let the smoke out, it got really hot. This one held up fine. It got hot, but it didn't break down at any point and performed well beyond its spec. Well, thank you both for being here. Brian and Michelle, this was a ton of fun.
It was a blast. Happy to be here.